horizontal axis wind turbine, the axis of rotation is horizontal, or vertical axis wind turbine. Okay, so vertical axis wind turbine, the axis of rotation is vertical, and so those vertical axis wind turbine had the advantage of, what do you think? What's the advantage of this vertical axis wind turbine compared to the horizontal axis wind turbine? Any clear difference or advantage in this? No, it's not surface area. Direction. Those vertical axis wind turbine don't care whether the wind is coming from the north, south, east, so they don't have to turn. The horizontal axis wind turbine, they care. They have to face the wind. And some people, when they look to those huge wind turbine, the one that's in the megawatt, they don't imagine that those things rotate. They do rotate, but they rotate slowly. Okay? They rotate, and actually it's really funny the way they rotate, because obviously they will have the generator on the top. The generator will be sitting behind those plates, and that generator generates electricity, and so there must be a cable coming from that generator, and that cable come into the tower all the way down to the ground so that it can go to the network. So do you see a problem now with that cable? So it can spin itself so that the cable will get basically stuck. So they wouldn't allow this. It spin to a certain angle, and then if you want to go any farther, it has to rotate from the other way. So the cable is always basically free. You don't really entangle yourself. But even those big ones rotate, and they have big motor with gears and stuff to make them rotate. But they are not like tuck, tuck, tuck. The one that do this is American farm wind turbine. You know, those are the ones that you can see them spinning with the wind easily. Right? It would be like this guy. Right? And even those have a mechanism that they wouldn't spin immediately. They have like a tail, and the tail is spring loaded, and then it takes, like, there's a little bit of mechanism so that it just not jump up and down, you know, like it takes there's a little bit of damping action into it. But anyway, so the horizontal axis wind turbine are basically, they need always to adjust their yaw angle, right? So, and those are the most common, because is it the most efficient? We'll see now. So the three-plated wind turbines are the most common. That's where you see it, basically in wind farms all the time. However, other exist. Now the vertical axis wind turbine don't require orientation. Also, they are very nice for small spaces, because they just like go vertically, and they have the advantage of having the wind, the generator on the floor. So when you have the generator sitting on the top and there is something wrong with it, someone need to climb, or a crane or something need to go all the way up to fix it, and that is a lot of cost, right, for maintenance. But if you have the big generator on the floor, you can just come and drive by and take things. You don't have to go all the way up to 100 meter or 80 meter, whatever the height of the hub, to remove the generator and put a new one or fix something. So they are nice in this. However, they used to have problem with stability, because as they rotate like this, what will happen? At a moment, like in one part, they are pushed by the wind. The wind is blowing on them, pushing them forward. But then when they go the other side, they are against the wind, right? So every one of those plates in his journey around the X, in one part of the circle, he's doing great, he's being pushed by the wind, but in the other side, he's actually moving against the wind, and that add drag, and that also add vibration, and those things will basically shake because of that. And so that's why they try to do those things. They try to put like a shield in the bad part of the circle. So when you are going against the wind, no, we don't want you to go against the wind. Let's put a shield against you. And then that shield need to be oriented with the wind direction. Then this guy loses the advantage of, I don't care where the wind is coming from, I will just spin. Now if you have something like this, you have to care where the wind is coming from, and you would have like a big tail that will adjust that shield so that he's always covering that part, right? There is also within those vertical axis wind turbine, there is the other distinction that some of them are drag based and some of them are lift based. So drag meaning that basically it's a half a cup, huh? Like the thermometer they put in the airport to measure the velocity, the thing rotates and they tell you what's the speed. So basically you are depending on the drag that is hitting that cup, and here you'll have more drag than the flow coming this way because the smooth surface of this side will allow the force on here to be smaller than the force on here, so eventually he will turn this way if the wind is coming in that direction. Right? Actually, even if the wind is coming this, he will always rotate in the same direction no matter where the wind is coming from. But the point is, he's depending on the drag, and therefore the maximum velocity of that plate is, what is the maximum velocity of that plate rotating around the X? His maximum velocity would be the wind speed. He can never hit a speed faster than the wind pushing on him. Okay? Is that like unique to drag based machine? Yes, because if you depend on the left, this plate that basically depend on the left, he can move way faster than the wind pushing on him. And I know this is hard to believe, but it is the truth, right? And so basically what I'm trying to say, that if the plate is like this, and here is the V, okay, and the plate is moving up like this is his U, so where would be W? W would be like this, okay? So W would be like this, and that generate lift over here and generate drag in this direction. So no matter how big this U is, even if that U is way bigger than V, U is like this, twice as big as the V, there will always be W. And this guy will generate lift. So he could be flying way faster than the V. The V is coming at 7 meters per second, and his U is like 21. And he will still generate lift. So he basically, what I'm trying to say is that he cannot escape from the wind. Because the way that, and that happened also to sailboats. Sailboats, if they have a crosswind, they will always move. And they could move faster than the crosswind that's coming on them. And they can never escape from it. But if you depend on the drag, like you are driving, you are in the Viking era, and you basically have this drag-based sail, and you just depend on the wind coming behind you, then the maximum velocity you can dream of is U equal V, because once you hit U equal V, relative velocity will be 0, and the drag would be 0. You cannot fly, right? There's no force. Okay? Right, so they will basically, their sail would be based on a left force, right? So you would be like here, but because he's moving this way, then this would be the W. This is U-boat, this is the V of the wind, and this is W. So this W over here would come like this, and it will generate left, which direction? Normal to the wind, and drag in the direction of the wind. So it is this left force, the horizontal component of it, is what will propel the boat faster. And this U could be huge, could be twice as big. Let me make it in better color. So this U could be like this, and because of the V, you will still have W this way. And you will still generate lift force, normal to it, and drag force. And it's this component that will push the plate fast forward. Okay? So left-based machines cannot escape from the wind, and they keep generating wind no matter what. Okay, but drag ones, they would actually have a limit to how fast they can move. Alright? So, having said that, lift machines are, this is actually based on lift, because those guys are airfoils, okay? So, but because of the vertical axis thing, in part of the circle, they are with the wind, nicely flying, generating lift, but then on the other side, when they are flying against the wind, that's when they start losing force, basically. They lose because they are flying against the wind. So the lift force generated on them, although they are airfoil, is actually not in the right direction. Okay? So it will oppose their motion. So, however, the problem with lift machines like this is for them to work, you need the U. You need the U so that, why do you need the U? So that W would be generated in the right direction. Okay? If you are not, if your velocity is just the absolute velocity, you may not really rotate that well. Okay? So that's why they couldn't really, sometimes they couldn't start. Because without the U, the W become the V, the plate is not designed for that angle, they will not rotate. And that's why you will see this. You will see they have a small drag-based machine inside, and this will always start. Right? The drag-based machine, it always start at, like basically with any wind, they will rotate. And so once this guy rotate, he will rotate the guy on the top or on the outside, and then the guy on the outside then could have like a bearing that basically allow him to go faster. So then like the smaller one would push him, but then once the bigger guy start moving, he can move away from the, just like the way you pike in your, right? Like the car can keep moving, exactly. Alright? Very good. And so people try to increase the performance of those machines by, as you can see. So again, this is an example of drag based, and basically left based. Right? And the drag based is, he's like trying to do 4 cups. Right? But by basically by doing half a cylinder and half a cylinder. And so people do research on, so you can maybe probably find the paper on, you look, should we make them exactly like this, or should we allow it like this with a little bit bypass between them? How much bypass? What's the effect of this? Should we go a little bit farther away, or should we go in? So there's all this geometry that people try to do, and also do we need a stator on the outside maybe, so that we let the flow come with a spin already rather than coming hitting the cup? There are all those papers about designing and improving. There's also a professor, I forgot, it was Arizona or Nevada. He got a lot of money by basically suggesting those vertical X wind turbine, when the flow leave them and the flow is spinning in this way, maybe we need to put another wind turbine on the down, and it's rotating the other way. And so you leave this guy rotating this way, you will push the other one the other way, and that improves the efficiency of the second one. So it was about how you stagger or rearrange the farm so that the performance is improved because of the weight coming from one to the other. Right?
Yeah. Did you set up like a reheat system almost? Like in a system?
So they are trying to improve the efficiency by recycling some of the flow coming behind, right? So there is a lot of improvement or a lot of innovation and a lot of patent waiting for you if you basically, because there is a lot of creativity that you can come up with. Okay, especially when it's pushing the limit of the efficiency. How you can design the efficiency so that it's really as close as possible to the maximum efficiency. Right? So this was talking about the plate from the fluid mechanics point of view. But if we look to this from the energy point of view, just like a black box, we will introduce the concept of CP. That CP is kind of the efficiency of a wind turbine. Okay, so what is the efficiency? It's CP is basically the power coefficient. C for coefficient and P for power. So the CP is power output over power input. Okay, what is the power output? The torque on the shaft times the omega. Right? You are basically this rotor eventually just move a shaft, and that shaft is connected to a generator. Right? And that generator rotates at omega and he has a certain torque. That would be your power. But now what is the power input? The power input is the power kinetic energy available in the wind approaching that big circle. What's the kinetic energy? Kinetic energy of my flying cell phone is half mv square, right? If he's moving at v and he has m, it's half mv square. Okay? So half mv square is energy, joule. But if you want to calculate the power, it's not half mv square, it's half m dot v square. So then it's not just kilogram times the v square, it's kilogram per second times the v square. So that will become the power. So half m dot v square, and m dot is the flow rate coming in that circle. And what's m dot? Rho AV. So half m dot v square is the input power. And the CP, that power coefficient, is power output divided by half rho or half m dot v square. What's m dot? Rho AV. So the v and the v square become v cube. So it become half rho AV cube. Make sense? Huh? CP is power output over half a rho AV cube. And that v cube is the reason why we get super excited when the wind comes from 9 meters per second to 10 meters per second, or from 10 to 11, because it's not like 10% increase. No, it's like v cube. Okay, so you can imagine 1.1 times 1.1 times 1.1, that 10% become very big. Okay, so now what is that CP value and how high it is? Here is the CP. This chart is for CP, and in our book, this chart is a little bit different. So if I give you those in the exam, I'll probably give this chart for you, because some of them are missing. I guess one of them is missing. But anyway, what's on the y-axis? That is the CP. That is our efficiency, kind of, huh? And what is the x-axis? The x-axis is how quickly this rotor is rotating. So, I mean, we can write RPM, but it's not dimensionless and doesn't really mean significant. Doesn't mean something important when you talk about small machine compared to large machine. So usually, in order to make those charts universal, they usually use dimensionless quantity. So rather than putting the RPM on the x-axis, they put dimensionless velocity on the x-axis. What's the dimensionless velocity? The omega r divided by u infinity. What's u infinity? The wind velocity. So the wind approaching at 10 meters per second, that's u infinity. The wind approaching at 8 meters per second, that's u infinity. And omega r, that would be the velocity of the tip. That is the tip. There is a hub and there is a tip, right? The hub is almost rotating at 0, but there is some radius, and there is a tip. And so this is the tip speed ratio, omega r over u infinity. And you can see the number. Okay? So what that tell you? It tell you that, wow, 8. The typical 3-plate wind turbine is flying at what? 7? 7. The tip is moving 7 times faster than the wind blowing on it. Is that possible? Yes, because it's based on lift. So again, no matter how quickly u is, omega w will always be there, and you will always generate lift. So you will be rotating at 7 times the approaching speed. Okay? And how about the drag-based machine? Can they move faster than the... Notice that Notice that this is just the tip. So the rest of the plate is moving slower than the tip, right? So you can see that this Savonus rotor, which is like basically drag-based machine, you know, he's like 1.8, 1.5, and that is when like he's doing almost zero power output, right? And that is only the tip. So, but the rest of the plate, of course, is moving slower, right? Make sense? Okay, and that is the American wind farm, and that is the Dutch windmill. Those are the big thing in Netherlands. So we look at our graph on page 70, and you will see that he put the American wind farm on the floor, and he put the Savonus on the top. Okay, so it's flipped. So if I don't give you the chart in the exam, you will use the textbook, but this is the correct chart, and this is what I'm going to give you in the exam. Okay? So what I'm saying is that those two guys are flipped in our textbook. Okay?
Is that an error? Should we correct it?
Yeah, it is an error. This is the correct chart. Alright? So now, interesting, all those guys are basically kind of following this arc for maximum efficiency. Okay? And those, although this is two plates and this is one plate. Right? But the maximum is basically, and for a lot of practical reason, people basically opt for the three plates rotor. And you can see what is maximum efficiency, 0.49. If you run it at that tip speed ratio, you go faster or lower, and the efficiency will drop. Okay, so interesting is this limit. Okay, and that is the limit of the theoretical maximum possible for a wind turbine, and it's called Betz limit. And the guy basically came up with this analysis that we will see in the next few slides. Basically said you cannot hit more than 59% for a wind turbine. If you Google, however, you will see there is like some papers that claim we hit the Betz limit. So that would be interesting paper if you can find it and put it in for our assignment next week. So now let's try to understand why it's 0.59. Okay, the ideal maximum CP. So if someone give you that job and he said we'll try to find out what's the maximum power we can get, and you are responsible for that, what do you do? What's your plan to get the maximum power? My plan is to find an equation for that maximum power as function of the things that change that power, and once I find this equation, I do what? Yeah, how do you find the maximum? Mathematically, how do you find the maximum? Yeah, you take the derivative with respect to whatever that thing that's changing or controlling that thing and set it equal to 0. And then that is the optimum parameter. Just like in the Belton wheel last week when we said here's the power as function of the u, and we set it to 0, and we figure out our u should be v1 over 2. That's the maximum power. So over here, his parameter is how much he will slow the air going through that wind turbine. So the velocity approaching coming in is VE, I guess, for entrance. I mean, if it was up to me, I would say V inlet and V outlet, but he called it VE for entrance and V O maybe for output or something. So obviously the velocity will slow down going through that turbine. Otherwise, what is this turbine supposed to do? It's supposed to eat the kinetic energy, right, and turn it into mechanical energy on the shaft, right? And we were talking about the environmental impact of wind turbine, and we said they are not totally green. Some people have problem with them. And so one of the problem is this, like people would say, well, if you change the, especially for big wind farm with like 400 wind turbine, if you slow down the velocity behind them, how does this affect the region behind them? Will slowing down the wind basically change the, the environment, like the ecosystem behind? But anyway, the point of one turbine is reduce the velocity. And so he's trying to figure out how much he should reduce that velocity. Ideally, you would think, let me reduce the velocity by, ideally you will reduce the velocity going through the wind turbine by how much? 100%, ideally. You'd say, let me kill all the kinetic energy. You are a customer coming to my place, I want you to leave with zero money out of this place. So you come with V1 10 meter per second, I want you to leave with zero. So we will see whether it should be zero, like really kill all or not. So he's basically saying you will come with C. C is the absolute velocity coming in. 10 meter per second, 7 meter per second, whatever that C is. And by the time you hit here, that plane, the plane of the disk itself, it's C1 minus A. That's how much we reduce your velocity. And by the time you leave, it's C1 minus B. Okay? And so he will try to figure out what is this A, how much is the A, and how much is the B for maximum power. Alright? So what tools does he got? What tools do we have in our thermofluid sciences? 3 equations. I always say we only have 3 equations. Bernoulli, which is an energy equation, and momentum equation, right? And continuity equation. Those are the 3 equations. And amazingly, those 3 equations is enough for you to have your name coined in every single book in energy conversion. And you will have the bits limit, or like if I did this 20 years, whatever, when he did it, would have been called Salam limit. Okay, so the bits limit basically was just done based on continuity, energy, and momentum equation, amazingly, and we will see this in front of your eyes right now. So he is gonna apply Bernoulli equation. So Bernoulli equation between the entrance and point 1. What is point 1? Just before the disk. Okay? Can we say that the energy here equal all the way to the energy at the exit? No, otherwise why does this turbine exist then? Right? No, the energy all the way at the inlet is not the same as the energy all the way at the exit. But the energy here and here just before the turbine is the same. And that's what you are seeing over here. Here's Bernoulli. P over rho plus half V square, or if you want to write it in pressure term, it's P plus half rho V square. We said there are 3 ways to write Bernoulli equation. You guys remember? You can write it like, that's not the good color. P plus half rho V square plus rho GZ equal constant, or you can write P over rho plus half V square plus GZ equal constant, or you can write P over rho G plus half V square over 2G plus Z equal constant. This has a unit of meter, this has a unit of joule per kilogram, and this has a unit of Pascal. Same equation, just different units, right? So he's writing them in which unit? Pascal. Excellent. So he's saying that if I'm comparing this and this guy, I will get this. Here is the velocity at the entrance, and here is the velocity at just before the disk. C multiplied by 1 minus A. Okay? And what is P1? That is the pressure just before the disk. And he will do the same thing from once you leave all the way till you go far away. Okay? So here is Bernoulli equation between 2 and the velocity is 1 minus a, and this is the velocity all the way at the end when it becomes c1 minus b. He doesn't know a and b yet, but he just wrote the energy equation. What's the other equation we got? Momentum equation. What does the momentum equation look like? Sigma of the forces equal to m dot v out minus m dot vn. And if it's the same m dot, you just write v out minus vn. Right? And that's summation of the force. And those forces are usually shear forces, pressure forces, body forces, right? So if we have only pressure force, it will just be B time area. And if it's in the positive direction, it's plus, and if it's negative, it's minus. Okay? Huh? This is the momentum equation. Forces equal m dot out v out minus m dot n vn. And that's what he did. So he's doing the momentum equation between here and here. So between here and here, there is no turbine. The velocity approaching and just the velocity before the plate. There is no turbine. So therefore, the only forces that exist is the pressure force here and the pressure force there. Okay? If I apply the Bernoulli equation between here and here, what forces does the fluid experience? Pressure force at the inlet, pressure forces at the exit, and the force on the turbine, right? The thrust on that tower that you are building need to take huge amount of force. That's why those towers are really strong, because there is a huge force on this tower. So that equation, that force will show up if I apply the momentum equation over the whole box from the inlet to the outlet. But if I apply between only this guy and this guy, there is no force from the rotor. I didn't hit the rotor yet. This is just before the rotor. And so that's why you see this. B entrance minus P1, right? B entrance minus P1 and equal to m dot. Where is m dot? M dot is rho AV. So here is the rho, and the A cancel with the A in the pressure force, and the V is 1c, and then the other c is the other velocity basically. So he's applying the momentum equation between this and this, and he's also doing it from 2 to the output. Okay, and you can see here is the velocity at the exit 1 minus b, and the velocity and the entrance 1 minus a. Okay, so now having those just continuity and just momentum and energy equation, and the continuity was the fact that we said m dot is the same as the m dot. Basically, I'm saying that the m dot here is the same as m dot here. That's why he's multiplying by the same m dot. From steady state, whatever kilogram per second coming need to be equal to the kilogram second leaving. Otherwise, the thing will blow up in a minute if he have discrepancy between the inlet and the outlet m dot. Okay, so just having the continuity, momentum, and energy equation in those two guys, you end up saying that B2 minus P1, that's the pressure before and after the turbine, equal to this. Okay, right? Summarizing or simplifying, it's basically, so why BO and BE was cancelled with each other? BO and BE, why they got cancelled? Because they're atmospheric. So really, really far away from the entrance is ambient, very, very far away. When you recover, it's ambient, but just before and just after, you can tell it's not going to be ambient. just after there's like wake and the pressure is lower, and just before you got basically the slowing down from the wall. The flow is basically slowing down, and he basically will increase the pressure on the plate, right? So he cancel BO and BE, and so here is the expression for the pressure. Now the momentum equation on the plate. Okay, so the continuity equation, the momentum equation on the plate will tell you that the pressure difference here is related to the force. Okay, and so he's saying that the thrust is the pressure between the before and after. That is the force on the plate. Okay, and if I apply the momentum equation over the whole thing from the start till the end, what do I see? Same pressure, but still I have high momentum at the beginning than the end. What happened? It must be the force. So if I apply the momentum equation, here is the place and here is the turbine, and basically this is B ambient and this is B ambient, and I still get C here and I get here C1 minus P. If I apply this equation between this station 1 and 2, I see reduction in the momentum because of not the pressure difference, because B ambient, it's because of the thrust that this plate will experience. Okay, and that is this equation. So he's saying that the thrust is m dot time the inlet velocity all the way at the beginning, C, and the outlet velocity all the way at the end, 1 minus P, and m dot is rho EC, and it's the same m dot through the whole system. So needless to say, we are tracking kind of a stream tube, so the flow that we have never basically leave us. We are tracking the same m dot going through the thing. So setting this equal to this, you will end up figuring out that A equal B over 2. This is the first breakthrough. So applying continuity and momentum and energy equation, he realized that A should be equal to B over 2. What is A? How much did you reduce the velocity here? So you come with C by this place, you are C multiplied by 1 minus A. And by this place, you are C1 minus B. Okay? And we just figure right now that B is twice the A. So if you drop by 10%, you will have to drop by the end 20%. But how much is the A? That's when he will do the mathematical trick of differentiating with respect to the A and saying it equal to 0, and that will tell him what's the optimum A. Therefore, he would know what's the optimum B, and if you know A and B, you figure out basically how much energy did the flow drop. And hopefully that will be the maximum energy that he can allow you to do. So he is doing, well, let me get the energy then. The change in the energy, delta E K, K for kinetic energy, the change in the energy between the entrance and the exit, that's what you are harvesting, right? So you started with, so he's changing, he's basically looking at the flow change between the inlet and the outlet, right? And so this would be half m dot v square. Okay, and after he got the delta E, after he found the EK, the energy that he's harvesting, he's differentiating it with respect to A and he's setting it equal to 0. So the results is A equal 1 over 3. Okay, so using this in here for A equal 1 over 3, you realize this is the maximum power. And dividing the output power over the input that we have, which is half rho AEC cube, 16 over 27, which is 0.59. And that is the best limit. And as you can see experimentally, also all those wind turbine that they have been testing, no one ever got closer to this. Okay, So now the question for a free quiz that I told you I was going to ask about last week. Remember what I said? Why this wind turbine, theoretically speaking, have a limit of 59%, but the hydraulic turbine we saw last week we saw with the charts basically showing that they can hit 95. So theoretically speaking, they can get 100%. That built-in wheel, if you make it at 180, you get 100% efficiency on paper. Yes, there are some friction, but this is also on paper. I mean, we didn't even talk about the friction on the rotor and the plates and the wake, and right? But why this is 59% and the other one is 95% or 100%? What's bad about wind turbine that it cannot hit the 100%? Anyone? Raise your hand if you know the question. Yes.
I'm guessing it's because it just can't, just the way it's designed, it can't take out all the energy in the games like we discussed.
So you are rephrasing my question. So let me ask the question in your language. Why does the wind turbine cannot extract all the energy from the flow just like a hydraulic turbine?
You the generators, next to the power,
It's not the generator, it's the rotor problem and the fluid problem. It's not the generator, it's not about storage at all.
Is it the fluid density?
No, it's not. No.
if within the moving fluid, if it would extract everything, and then it could flow. Right, like the velocity at the end is zero, then there would be no flow, and there would be no generation of power.
You are that close if you explain to me why this was not the case for the water. No. So, I mean, Devin hit really the right place. Kinetic energy is not extracted to the fullest, because if we do, it will not leave. He's right, but why would the hydraulic turbine manage to extract to 100%? Doesn't hydraulic turbine also have the same problem? They also, if we slow down to zero, they will not leave. Pit's limit, yeah. We are trying to explain why that pit limit does not apply to hydraulic turbine.
Because the waters are connected through the turbine where the wind turbine is spoken in.
No, I don't think the confinement of the tube is really the reason. So let's listen to what Devin said again. He said that if you slow it down to zero, it wouldn't leave. Yes, but why would the hydraulic turbine wouldn't suffer from the same problem? Why the hydraulic turbine, if you slow it down to zero, why it still would leave? If you answer this, you get your free quiz. Jairo.
Really because of the direction, the flow in this case is moving horizontally where the water moves with gravity. So it would still go through the actual turbine as it's designed vertically.
So I'm gonna give you the free quiz, but it's not because it's the vertical horizontal, it's because of gravity. Water, if you slow it down to zero, will still fall and get out of the way. But air will not fall. He doesn't have anywhere to go. He will stay there. But the water can fall down and get out of the way, even with zero velocity. So the thing with water, you leave with zero kinetic energy, but you still have potential energy that will take you down, right? But the air does not have potential energy because he doesn't have density really that much, and where would he go, right? But water will go down. Alright, so we explained then the fact that water has still have potential energy that allows to drop, and so you can slow it down to zero and still get the maximum power. But for wind turbine, it cannot leave. And so then if you are lucky and you find that paper that say we just invented, there was this paper that it say we invented a rotor that end up hitting higher than the bits limit. Then check the analysis and see why they managed to make it out. How did they manage to make the flow leave even with velocity lower than the maximum allowed, lower than the lowest allowed. Alright? Very good. So this chart is basically showing us the places where people have a lot of energy, and we are lucky enough in North America, right, to have all that place. The only bad thing about this is, about our place, is that the energy is available in a place where there is no people. So the people are in the East Coast and the West Coast, and this have very low density. So then the solution is production line, or like basically like transmission line that take the power to the market where it's needed. But that has to go through land, and the people who has the land don't like it. And so they were planning to build like a huge farm. PSO here was planning to build a huge farm in West Oklahoma, but to harvest that energy, but it was basically shut down because people said no, we don't want in Oklahoma we like oil and gas, and we don't like wind energy that much, and also we don't wanna things go through our farms, and so the thing was still, there was a contract office in Chicago that was responsible for designing the farm, and I forgot how many, 400 wind turbine or something. It was gonna be huge, but it was shut down based on that people basically objected. Alright, so again a better chart. And we saw those last time. We said that it can even more if you go to the offshore, and people are doing that already. Right? The other trend is the economics of scale. So this slide basically explained to us that the bigger the wind turbine, the more you will make for the dollars that you invest in it. Okay, so you can harvest back your investment much quicker if you build it really big. So the trend is to make them bigger and bigger and bigger. Okay, so economics of scale. So you can see, you know, this just is the casting. Here is one guy and here is the plate. Okay, and this is interesting, like how do they move those big plates from one place to the other. And if you are a friend with me on Facebook, you will see there's a video on Facebook showing basically how does this, like when they go over bridges and stuff, you know, how do they manage to actually go through it. It's really, really hard to move them around, especially in European cities, because they don't have the space that we have. So it's very challenging to move it over there. Alright, so this is a good place to stop. So let me stop here for 15 minutes and we will come back at 7:50. So 15 minutes break.